Okay, so our last talk is another talk on FPGAs from Spenser, Gilliland.
Hi, my name is Spenser Gilliland. I'm with Xilinx, and I basically spent the past couple weeks coming up with this SHA-1 optimized for FPGAs using OpenCL. It's been a great experience, and we've got some good numbers to show. Just an agenda of what we're going to go over. A little bit about OpenCL and FPGAs, really just describing the architecture that this specific board that I'm working on is using. I'm sure some of you have seen the presentations from earlier in the week, and I only have 15 minutes, so I'm going to cut down on that. A little bit about how SHA-1 works so that you can understand the optimizations that were made, and then the optimizations, and finally a comparison. So the board that I was using in our comparison, in our work, was the Alpha Data PCIe 7v3. This is a PCIe X8 board with 8 gigs of memory. There's a total memory bandwidth of about 21.2 gigabytes per second. On the board is a Xilinx Vertex 7 VX690T FPGA. The numbers are there for a comparison of how big this device is. It's a fairly high-end device, so it's got lots of space. A little bit about how SDAcccel splits the design. So there's a static region that contains the memory controller and the DMA controller. And this is fixed as you turn on the platform. So there's no changes that occur to it. There's a smaller region called the OpenCL region. And this is where you instantiate the kernels. This is where, whenever you call CL create program with binary, this is where everything gets installed and your computation is performed. So a little bit about SHA-1. SHA-1's a relatively old algorithm. It's been around since the 90s. It basically takes a 512-bit block and turns it into a 160-bit secure hash. It starts off with 512 bits of data coming in and a previous state coming in. It then processes it and then spits back a new state. And so if you look at this algorithm, it's very cyclical. You have data coming in and a hash coming out every single cycle. There's 80 rounds total, and most of the operations are basic integer operations. The code we used is from OpenSWAN. So a little bit about how we decided to design this. We're basically going to use 2 SHA-1 compute units, and the way we've created them is to try to limit the loop carry dependency as much as possible, and we do that by pipelining as deep as possible, and then by replicating those pipelined units multiple times. And so that's why there's 2 units there. The memory interface is another issue. So if you think about how the SHA-1 compute units are connected to main memory, there's an interconnect that is the arbitrator between the various compute units. Now this interconnect in our system is 512 bits wide, so there's no way of pulling in any additional memory through that interface. So what we need to do is make sure that the compute units have a 512-bit interface and that they're able to access the full bandwidth available. So one of the first optimizations we did is add this 512-bit parameter to our device. And another thing we did is we decided, well, if we're going to go to main memory for the data, then if we have to go back to main memory for the state, that's going to be contention on the bus for the DDR. So we decided to put the state of the program in program scope global memory. And what this does is it basically is a program global memory that is accessible from the compute units. It is only accessible from the compute units. It's not accessible from the host. But because the state is basically just wrapped around multiple times, it's better to have it in this way because then we can have lower latency and higher throughput access to this specific variable. A side effect of this is that to access the program scope global memory, to pull the state out or to reinitialize the state, we had to have a utility kernel. And basically all this kernel does is initialize the program scope global memory or pull out the final hash from that memory. So the major goal of this was to see what kind of performance we can get. And performance was really based on the total throughput. So we're doing multiple SHA-1 channels at a given time, a total of, let's see here, 2 times 83. So there's 160 odd channels that are used. And for each channel, it takes 112 clock cycles to go from the data coming in, the state coming in, to a result that is the new state. And you can kind of see here, this is one of our reports. The iteration latency is the total pipeline depth, and the initiation achieved is the time between iterations of the kernel. So if you have a kernel and it takes 4 cycles to read the memory, you're going to have to wait 4 cycles before you can read another block of memory. So if you have an initiation interval of 1, that means that for every cycle you can pull out 512 blocks of memory, or 512 bits of memory. In our specific case, you can pull out 512 bits of memory. And it'll do that every clock cycle, which equates to approximately 12.8 gigabytes per second of bandwidth. So the other issue that we had to look at was trying to minimize overall latency for a given length of a SHA-1 input block. So if you have 8,000 characters coming in that need to be hashed, you actually need to go and do the first 512 blocks, and then you immediately need to get to the next 5 blocks and immediately to the next one and so on. Now the problem is that operation takes a very short amount of time. In a given FPGA, this is going to be on the order of a couple of 500 nanoseconds or so. And if we need to actually re-init the kernel every single time, that's going to be ineffective. So one of the things that we've also done is implement a cache inside the compute unit that holds the local state during the kernel execution. And what this does is it takes the incoming state, initially stores it, then it processes the data using the SHA-1 algorithm, outputs back to that state, does it another block, another block, another block, and finally, at the end of all the blocks that have been processed, it will output the state back to the program scope global memory. This ensures that we get the highest performance and that no additional memory accesses are required. Additionally, the state, which is a 160-bit wide array, we had to cyclically partition that specific variable. So that just makes it so that there's multiple BRAMs backing that variable at any point in time. This allows full parallel access to the variable. The same was done for the block coming in. So overall, we found that the resource usage of this compute unit was approximately 6%. That's not very much. So with 6% of the device, we can consume 12.8 gigabytes of memory bandwidth. And this is an entirely memory bandwidth limited algorithm. So if we're going to use the full bandwidth available to us on the system, we could at max implement 2 of these SHA-1 compute units. However, if we get to a situation where we have a larger memory bandwidth, and this is something that we don't have currently, but we're looking at other types of memory, the theoretical maximum that this compute unit design could provide is 204.8 gigabytes per second. So these are more or less back of the envelope calculations, but this is pretty much what we'd expect in this given situation. So for an Intel Haswell CPU, the best published results I found are 5.8 cycles per byte for a SHA-1 computation. On our implementation, we're doing 64 bytes per second, so that's 1.56 cycles per byte. On the alpha data, 200 megahertz clock, Intel 2.0, 12 cores, 2 compute units. Overall, we get about 4.14 gigabits per second total bandwidth from the CPU is what we'd expect. And at approximately 100 watts total dynamic power, so we're derating the CPU just a little bit here because I think this part is about 120 watts total. We get a total gigabytes per second per watt, 0.041, which is not too bad. However, when you look at how you can actually do this on an FPGA, you can get much better performance. In the alpha data case, we're seeing a 25% improvement, or we'd expect a 25% improvement. And in a non-memory bandwidth limited case, which is possible, we'd see a 200 times improvement. All right, thank you. Any questions?
I'm a little bit puzzled by the non-memory bandwidth limited case. How do you make that happen? Is it magic?
It's an estimate. So given that the number of utilization presented here, 6% utilization of the FPGA for the maximum, there could fit 16 compute units in the device. Given that there's 16 compute units in the device, there would be 204 gigabytes per second of memory bandwidth required by the application.
Yeah. No, I get that bit. It's just, as far as you can tell us, there isn't actually any way of getting 200 gigabytes a second into the FPGA, right? So this bottom right one isn't really, it might be kind of theoretically interesting, but
yes, it's a academically interesting thing. But no, it's not something we currently have.
Yeah, we could say the CPU can have more memory bandwidth or more cores or something.
But it wouldn't help the CPU unless the CPU had significantly more cores.
But it's a memory bandwidth bound problem.
Not on Intel. Not
Really?
According to this. It's 5.8 cycles per byte, and there's 12 cores. Then there's only 4.14 gigabytes per second that can be done. So you'd have to have significantly more cores. It's memory bound on the alpha data card and on the theoretical FPGA. But it's not memory bound on the CPU.
And I guess you said those are the best figures you found, so you
Yes.
kind of have to take it at face value. It feels slightly fishy, I have to say. Generally, if you can get to some good fraction of memory bandwidth on one platform, there has to be a damn good reason why you can't get in the same ballpark on most of the platforms, unless there's something radically different about the way it's implemented.
Yes, so if you look at how an FPGA is implemented, it's a fully pipelined 80-cycle loop that's actually occurring during the optimization phase. And so every single time the clock ticks, there's 64 bytes of data being processed. So if an Intel architecture had a 64-byte wide SIMD component, then it could maybe do a little better. But I mean, that's something that probably doesn't make sense for the general use case. So this is just one way that FPGAs have a small advantage because they can create these massively parallel pipelines.
Okay, thanks.
Any other?
How long did it take to compile the program you were dealing with?
The program we're dealing with, I think it took 30 minutes to compile it, to synthesize it completely.
Other questions? Okay, let's thank our speaker again, and then Simon's got some closing remarks.
Thank you.
Presentation.